Hi everyone, I'm Hewan Seo. I will present our paper on DSNet, Dynamic Skin Deformation Prediction by Recurrent Neural Network. The other authors of this paper are Kaifeng Zhu from Université de Strasbourg and Frédéric Cordier from Université de Haute-Alsace. Realistic dynamic skin deformation contributes to the realism of character models in rendered scenes. It has a long tradition in computer graphics and computer animation, which is evidenced by the large amount of research done on skin or soft tissue deformation. Since its introduction by Nadia Manina-Tellman in the early 90s, the linear blend skinning, or LBS, has become a well-established method for obtaining the skeleton-driven deformation of a character. It involves first defining an underlying skeleton, associating then each or a group of vertices on the skin mesh to their nearby bones, and deforming the skin mesh by applying to each skin vertex the weighted sum of the rotation matrices induced by its associated bones. Although LBS is still a golden rule which is practiced in many different places, it has several limitations such as unnatural deformations at certain poses, including candy wrapper effect or volume shrinking effect, its impossibility to express nonlinear deformations such as muscle bulging, and finally, and most importantly to our work, its impossibility to simulate skin dynamics such as jiggling effect. So a large body of previous works has been devoted to propose solutions to these problems, which can be categorized into geometric, example-based, and physics-based methods. Geometric methods propose to replace metric representation of rotation by mathematically more desirable representations such as quaternion or log metrics, while keeping the simplicity of the linear blending scheme. Example-based methods are basically based on a sparse set of quality shapes, which can be leveraged by a scatter data interpolation. Physics-based methods aim at obtaining high-quality results by modeling the anatomical components of the body, consisting of individual bones, muscles, and soft tissues covered by a flexible skin. One remarkable recent trend along this line of research is the data-driven approach to the modeling of human body shapes. By using hundreds of scanned shapes of real people under correspondence, a so-called shape space is constructed, where a shape instance is represented by a small number of weights to basis shapes. Earlier models have focused on the generation of identity shapes by learning mathematical models relating the model parameters to the person-specific shapes. More recent models incorporate both subject-specific and pose-dependent shapes into a single unifying framework, allowing the generation of new post-body shapes at an interactive time rate. Despite these efforts that can achieve realistic skin deformation at static poses, little attention has been paid to capturing and learning the dynamic skin or soft tissue deformations. Recent attempts to model the dynamic human shapes have also deployed learning-based methods, as have shown in DINA. In that work, they try to model the human shape exhibiting dynamic skin deformation as a combination of linear component and a residual one. The linear component models the identity and pose-dependent part, which is basically the linear blend skinning as a function of pose vector theta. And the remaining residual, including the dynamic skin deformation, is modeled as a function that takes inertia parameters such as velocity and acceleration, and the residuals of two previous frames as input. In our work, we model the dynamic skin deformation as a sequence data. We deploy a recurrent neural network, notably an LSTM network, to learn a function that takes a sequence of pose vectors as an input and outputs a sequence of skin displacements. One improvement we make over the previous work is that we do not require to compute the inertia-related parameters and directly use the pose vectors as input. Another improvement made by our work is that we do not limit the number of previous frames influencing the current frame to a predefined constant. Instead, it is modeled as a learnable parameter through training from the data. We also consider the subject specificity of our model, meaning that we want the function to predict different skin displacements depending on the body characteristics. So our function can be written as a function of theta t, the pose vector, and the f of theta t minus 1, its output from the previous time step, and the beta, the identity shape parameter from the simple model. As some of you may have guessed already, we use simple model as the common shape space. Our dataset comes from the DINA work by MPI, composed of 5 subjects, each performing 10 to 14 motions, exhibiting some dynamic skin deformation. They are all in pointwise correspondence with over 6,000 vertices. And each motion performed by each subject comes in a different time duration, varying from 2 to 15 seconds. DINA dataset is rather limited in size, so we have tried to maximize the use of this data for training the network and find some extra data set for the test. Another related work, MOSH, provides some dynamic skin-inducing motions that are not included in DINA. We could use some of the mesh sequence data in MOSH as our test data, after resolving the problem of different sampling rates and the global orientations of the two datasets. DINA dataset is rather limited in size, so we have tried to maximize the use of this data for training the network and find some extra data set for the test. Another related work, MOSH, provides some dynamic skin-inducing motions that are not included in DINA. We could use some of the mesh sequence data in MOSH as our test data, after resolving the problem of different sampling rates and the global orientations of the two datasets. The generation of training data is done by finding the best matching simple parameters through optimization and by saving the residual skin displacements for each mesh in the dataset. It is done in a sequence-wise manner. For each motion sequence M in the database, we proceed in the following manner. We first compute the best fitting simple parameters beta and theta at frame number 1. Then for each of the remaining frames, we consider that the beta we found at frame number 1, which is denoted as beta star, remains fixed. And we compute the best matching theta value, theta t. Once we found the error minimizing beta and theta at each frame, we take the difference between the data mesh and the simple model at rest pose. And this is what we take as the dynamic skin component, which is used as training data together with the found beta and the theta values. This slide shows an example of the results we obtained through the mesh alignment process I just described. A is the data mesh. B is the same mesh at its rest pose through the unposing function, the inverse of the linear blend skinning. C is the best matching simple model found by the optimization. And the per vertex displacements between B and C, the residual skin displacement, is illustrated in D as a color map. The lighter is the color, the larger is the skin displacement. This slide shows the architecture of our DSNet. At the core of our network is an LSTM, which has been chosen for its ability to learn over sequence data with its memory on its previous predictions. Our DSNet takes the body shape vector beta concatenated with theta as an input and generates the nonlinear dynamic skin deformation at each time step. The fully connected layers at the beginning learn to extract the latent inertia features from theta Thus, we do not need to compute the angular or linear velocity nor the acceleration, unlike in DyNA. The dense layer at the end maps the output from the LSTM network to a low-dimensional feature vector, delta, in the latent space of dynamic skin displacements, which has been pre-trained by an autoencoder. The original skin offset, delta, large delta, will be reconstructed by the decoder network of the previously trained autoencoder. So this is our displacement mesh autoencoder. The encoder is composed of 2 fully connected layers, followed by 4 convolutional layers of 1 dimension, and the last linear layer. Here the gray box represents the data with its size denoted on top and bottom left. The first 2 fully connected layers gradually increase the feature description of each vertex from 3 to 64 and 228. The subsequent CNN layers output lower resolution representations of the displacement mesh while keeping the feature dimension. The last linear layer learns to map the lowest resolution representation to a feature vector of size 100, which serves as the intrinsic representation of the skin displacement. The decoder takes the symmetric structure of the encoder and reconstructs the original skin displacement from the feature vector. Some of the implementation details about our displacement mesh autoencoder is given on this slide. In particular, compared to the other autoencoder by Casas and Otadui, which is composed of 3 fully connected layers of 6,000, 3,000, and 100 outputs each for the encoder and the symmetric decoder. Our autoencoder amounts to only 12% of network parameters, which is much more time and memory efficient to train. This video demonstrates the reconstruction results by our autoencoder. From left to right, the ground truth, the network output, the output of the autoencoder, and the per vertex error coded in color map. Another reconstruction results are shown in this video. The maximum error has been 1 centimeter in this case. Implementation details on our DSNet is listed on this slide. And let me briefly mention about our data preprocessing. Although spatially coherent, each motion sequence in DyNA dataset comes with a different number of frames. To feed in as input to the neural network, these sequence data need to be rearranged as a multidimensional tensor of a fixed shape, which means we need to uniformize the number of frames of all motion sequences. Based on this histogram of motion clips according to their frame length, we heuristically chose a frame length of 300 and zero-padded at the end for shorter sequences and tail-clipped longer ones. This video shows the results we obtained on the validation data, a motion sequence that has not been seen for the training. The chosen subject's other motions, as well as the semantically identical motion from 4 other subjects, have been used for the training. The predicted dynamic skin displacement, when added to the simple model, which is on the rightmost side, faithfully reproduces the original skin shape shown on the left. In this video, we show the dynamic skin deformation predicted by our network for a known subject undergoing an unobserved motion. We observed that our DSNet can also make plausible predictions for semantically new motions and new subjects. To conclude, a learning-based method to the estimation of quality dynamic skin deformation has been proposed. The dynamic skin deformation has been modeled as a function of pose, body shape, and the results of previous time steps. For that, an LSTM-based neural network has been developed, trained on sequences of triangular meshes captured from real people. Also developed has been an autoencoder, which builds a compact space for the intrinsic representation of skin displacements, allowing a very efficient operation of the proposed DSNet. Thank you for your attention. This project has been supported by a French national project, Human 4D.